Okay, so let's have another problem. A 6-meter simply supported beam supports a uniformly distributed live load of 15 kilonewton per meter and a dead load of 10 kilonewton per meter. Self-weight already included. Applied on its entire span. Using FC, that is 9.3, and Fs is 124, and then you have your N is the modular ratio, that is 9, and the base given is 200 millimeter, and the diameter of the reinforcing bars is 20 millimeter, and also the cover is 60. You are to design the beam and also determine the required number of reinforcing bars if it is only reinforced in tension. So for the simply supported beam, the tension portion is at the bottom of the beam. Okay, so for the solution for by the way, for the beam, you have a 6-meter simply supported beam. You have a hinge and a roller support, and then you have the distributed load W. So for the distributed load W, you are given a live load and a dead load. Okay, so to solve for the total W, we have the distributed load due to live load and dead load. For the dead load, that is 10. For the live load, that is 15. And for the maximum moment, you have the maximum moment. You can solve for the maximum moment using shear and moment diagram, or you can have the formulas. I already assigned to you the formulas for the maximum moment for simply supported beam. So for the simply supported beam with the distributed load, you have the maximum moment, that is equal to W times L squared over 8. Okay, and if ever you have the concentrated load P, usually that is at the center, so your moment is PL over 4. But for this problem, we only have the load W. So we'll have our applied moment, or the maximum applied moment, which is equal to WL squared over 8. So substitute the values. For the applied moment. You have W, that is 25, multiplied by the length, which is 6 squared over 8. And then you have the units in kilonewton for this one, and then 6 meter squared, and 8 over 8 meter. So you have the applied moment equal to 112.5 kilonewton meter. So convert kilonewton meter to Newton millimeter. So that is 1000 millimeter over 1 meter, and then times 1000 Newton over 1 kilonewton. Cancel. So you have 1 million Newton millimeter. That is 60, that is equal to times 10 power of 6. Okay, so you have now you have to solve now the resisting moment first for concrete. So MC, you have 1/2 FC kg BD squared. You have your MC equal to your applied moment. That is 112.5 times 10 power of 6 Newton millimeter. And then you have your FC. So not FC prime but FC. That is equal to 9.3 megapascal. To convert that to Newton per millimeter squared, so that is just equal. So megapascal is equal to Newton per millimeter squared. And then the base is given, which is 200. So this is design problem. So you have the formula for your K. So we are given the value for N, that is 9 over 9 plus 124, that is the Fs, and the Fc is 9.3. So our K is equal to 0.403. And then we will solve for J. Formula is 1 minus K over 3. We already solved our K, that is equal to 0.403. So now we have our J is 0.866. So substitute the values. You have the formula for MC. MC is equal to MA, that is 112.5 times 10 power of 6 is equal to, of this formula, substitute the values, 1 half times 9.3 times 0.403 times 0.866 times the base, which is 200, times the D squared. So D is equal to, that is the cube root. I know. Squared only. So square root. So therefore, you have the square root of 2 times 112.5 times 10 power of 6 divided by 9.3 times 0.403 times 0.866 times 200. So now you have your D equal to 588.73. Round it up to 589. So you have now your D. And then we will solve for the resisting moment of steel. You have the formula. MS is equal to AS times FS times J times D. So MS, that is also equal to MA, or the applied moment, equal to 112.5 times 10 power of 6. And then we have the Fs given the problem. In the problem, you have 124, and then J, we already computed it. That is 0.866, and the D, that is 589. So substitute the values. You have this formula. So MS is equal to 112.5 times 10 power of 6. And then we will solve for AS. Then Fs is 124. J is 0.866. And D is 589. So our AS now is 1,778.68. So that is now the required total area of steel. And then to solve for the number of bars, we'll have the formula NB is equal to the number of bars, the area of total area of steel in the formula MS AS FSJD divided by the area of 1 bar. So the AS, you have 1778.68 divided by pi over 4 times 25 squared. Okay, so the answer is 3.6. So therefore, round it up to 4. So even if that is 3.1, so always round it up to whole decimal or whole number. Whole number. Okay, now, so draw the section and the spacing of or the orientation of your bars, and then compute for the spacing. So to compute for the spacing, you have this one. Given B is 200, and then the side cover is 40, and then you have 4 bar diameter and 3 spacing. So you have your answer equal to 6.67. That is less than 25. So therefore, you have to rearrange your rebars. Okay? It is 2. So you have to rearrange. This is SB. Then 40 and 40. So therefore, you have this formula. 200 is equal to 2 times 40. That is the side cover. Plus 2 times 25 plus SB. Now you have your SB equal to 70. 70 is greater than 25. 70 is greater than the bar diameter, which is 25. And also greater than 1 1/3 of the maximum size of coarse aggregate. Therefore, you have to place the bar in 2 layers or in bundle. So that's the design answer.